Okay, we are live. Okay, so today we will be seeing a little bit about signal processing. Processing. I wrote it right. Let me check. No. Okay, we will be seeing about signal processing. In particular, we will be seeing denoising. That is something that we have seen previously, but now I think you have more tools to understand and maybe do it on your own when compared to the previous time. And in particular, we'll be seeing signal denoising or removing the noise of a signal by using the least squares approach. Brief reminder of what you have seen until this day is that you have already seen what the adjoint of a operator is and how it is related with the transpose of the matrix that represents the linear system. And before the TA, we briefly mentioned that the transpose of a vector can be used to describe the inner product. And we briefly mentioned something about the gradients or the derivatives of a function or a multivariate function. Okay, so let's talk about signal processing. First, let's remind a little bit about the least squares problem. If you have a space here, V, described by some vectors, V1 and V2, or more vectors, it doesn't matter, being B, the range of the basis, or the space is the one determined by all the linear combinations between the basis vectors. And we had a signal, for example, B. And let's say that in our case, this space represents a space of smooth signals. So for example, if we plot B as a function in time and each sample is an element of the vector, we have something like this. But we wanted to represent the vector in a smoother space. For example, this one. How, so this blue line is the vector here. Let's call it, how can we call it? Let's just call it Y. That is the closest vector to V in the smooth signal space. Do you remember how can we get this Y in function or by using these vectors V1 and V2? Put this to the side. Yes, it's a linear combination, but it's a linear combination with a special name, the orthogonal something projection, right? So by solving this least squares problem, we are basically obtaining, or we can obtain the solution by using the orthogonal projection. Okay, so the orthogonal projection, in this case, y, can be written, I'll just use two vectors to make it more simple, as a coefficient, in this case, x1 times the vector v1 plus another coefficient x2 times v2. So basically I'm trying to write my noisy signal. Oh, sorry, here I used colors that I didn't mean to. So this x, let's put it like this in orange. It will be this one. The v, it will be red, and the matrix A that contains the vectors v1, v2, and so on is this one that is in light blue. Okay, so we can describe this y, that is the orthogonal projection of v, by using a linear combination of the bases. How did we get these coefficients? Yes, we did something like, for example, for x1, it will be v1 x divided by v1 v1. For this one, it would be v2x, sorry, v2b. B and v2 v2, right? So that was the first way we had to do it, but later we presented that this can be solved equivalently by using something called the normal equations. And that was mainly because we have the A, the coefficients x, and we wanted this to be equal to b. The b was the red function, but we had a residual to make them equal. So basically, to remove this residual, we had to take into account that this residual is perpendicular to the range of this, or is perpendicular to b. That means that if we applied the dot product with all the different basis vectors, basically we remove the component r, and that is exactly the same as applying a transpose from the left. By doing this, basically I'm doing this part here, and we saw that this is equivalent to applying v1 transpose r, v2 transpose r, vn transpose r, and as r is perpendicular to the whole space, it will be perpendicular to each basis vector, and that means that the dot products will be 0, therefore eliminating the contribution of the residual, and we arrived to the normal equations. So the normal equations help us to solve the least squares problem by basically deleting the contribution of the residual, that is this vector here, that is perpendicular to the space. Right? Are you following me? Yes? You have seen this in another TS, but we're repeating it to make it more clear, and maybe now that you know what the transpose and all these different notations mean, you can understand better why this is equivalent to this and how we can remove the residual. Okay, so now we have the normal equations. That is a system that can be solved, and actually, as the A transpose times A is a square matrix, independent of how A is, we can try to at least do the inverse. So if everything's right, we can do the following operation. That is basically the solution of the least squares problem and also the normal equations. And everything here, it's called the pseudo inverse. So we had our connection between the normal equations, the pseudo inverse, and the least squares problem, right? Three things that are connected and basically are the same. All right. And that's how our transpose appears, because we are trying to do multiple dot products at the same time to solve the least squares problem. And then we have our solution that is explicitly the pseudo inverse times the vector v. Okay, so this is only our vector of coefficients. So now to get the orthogonal projection, or the vector y that represents our denoised signal, we need to multiply these coefficients that we got by solving the problem times the matrix. So we got this here. All right. So now we'll try to do this with Python, if there's no doubts. Everyone understood this completely? No? Could you okay. So the orthogonal projection is this vector here that we represented as a linear combination of the basis vectors. This is the vector we are interested in. That is the denoised signal. This is the denoised signal. But by doing all of this with the normal equations, we only got the vector of coefficients, x1, x2, so on. This x. So to basically get the vector y that we are interested in, we need to multiply by the basis that is represented by this matrix A. So a times x is the same as this, because a has in each column a basis vector. And basically here I have my vector of coefficients, x1, x2, xn. And you can see that this is, for example, let's say that this is n by n and this is n by 1. You multiply each row by this, and you do the same with every row, basically getting that x1 times b1 plus, and here maybe I can copy paste this, like x2 times b2 plus dot 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 and until n. So this is x2 b2 and this is vn xn. Please remember that these v's are vectors. I didn't put the arrows, but these are vectors, and these x's are coefficients, just numbers. So we are doing a linear combination of vectors to get another vector that represents our function y. So basically, by solving the least squares problem, we are solving to get the coefficients. The solutions are the coefficients, but we don't want the coefficients, we want the denoise signal, so that's why we need to multiply by a. Okay? Yes? Clear? Should we start with the Python? Okay, so first I'll start by importing some functions. For example, in space, cosine, sine, phi. What? Ah, I forgot to start the Python. There you go. Can I copy? Okay. And also from matplotlib or plot. Here in pyplot. All right. So now let's fabricate our noisy signal. For example, let's say that our noisy signal V is equal to, let's import from numpy, import from numpy that dot random import and n. Yes. So V equals to, for example, cosine. Let me create our times first, line space from 0 to 1 with 100 samples. Then V equals to cosine 2 pi t plus rand n of 100 v dot shape. Okay, And if we do plot, forgot to import show. There we have our noisy signal. Maybe too much noise. Let's make it a little bit less by multiplying this by 0.1. And we're going to increase the frequency a little bit. Okay. So we have our noisy signal here, B, that is represented by a sinusoidal function or cosine function. And we have noise due to the sampling that, or the machine that is a little bit noisy. This is something that is very common to add Gaussian noise. That's what I did here by using rand_n. I'm basically adding Gaussian noise. We haven't seen what that means exactly, but it's a very common type of noise, also called white noise. But maybe this function that we acquired is not enough to do our pipeline or processing. So we need to do denoising. And how we can do that? By applying this thing here. So we are basically trying to solve this problem. Okay, so now we can close our plot. Now, how could we create this matrix A? First, we need to import from numpy import concatenate, then A equals to concatenate of, for example, cosine 2 times pi times an index. Let's put this index as frequency so it's more clear. And then for I in range, 100. And this will be concatenated in the axis 2. F not defined, sorry. Sorry, 1. In Python, we started from 0, so the second axis is the axis 1. Shape. Come on, 1. There you go. So A shape, 100 to 100 times 100. And if we want to solve the least squares problem, how we could do it? With the function least squares. Okay, if we do that, we can get the vector coefficients between least squares of A comma B. But let's remember that the first element of this is the solution and the other one is the residual. We are only interested in the first element. It says a warning, but it doesn't matter. It's solving the problem regardless. And now to get our vector y, we had to do A dot product this vector coefficients x. There you go. So now we do plot the original signal and the noise signal. And we do show. We have that it is kind of better, but not so much. And that is because we are trying to solve the least squares problem with a basis that it has too many vectors, or vectors that has too many changes. The cosine with frequency 100 is a very rapid changing function. So that's not good for denoising because it can fit the noise correctly. Now, what happens if A, instead of going to 100, goes to 50? And we solve exactly the same problem. And we plot the results. Show. It's a little bit better, but still not enough. Now what happens if we put 10? Solving the least squares problem. Then in our orthogonal projection, plotting the results. And as you can see now, we have a function y that is smooth, but the original signal was not smooth at all. And that's basically because we restricted our solutions to a space of signals that are smooth. If we see this, or the space of the basis functions, we see that we have a cosine with a very low frequency, we have another one with increasing frequency, but if we see, for example, the last two basis vectors from -2 to -1, for example, we see this is the maximum rate of change that our function that is the noise can have. So if the noise changes faster than this, basically it can't be represented with this set of vectors, and therefore doing a smoothing of the function. So just to write it out, if we had our vector v that was very noisy, we are trying to write this by using signals that are, for example, x1 times the first basis function that is something very smooth, plus x2 times something that changes a little bit more, x3 times something quicker, but it is not enough to fit the noise. You can see that if we decompose the signal in the noisy and the clean part, it is a very clean signal plus something that is noisy. Our basis functions can only fit the noise-free part of the signal. The noisy part cannot be represented by this basis. That is another way to saying that is that the noisy part, let's call it n from noise, is not present in the kernel of A. So the noise cannot be represented by our basis vectors, v1, v2, v3. If it can be represented by our basis vectors, it will be no gain in doing this denoising because you'll basically have the same signal. Are you following me? Should I explain something again? Okay, so in Python, for example, if we plot the difference, it would be b minus y. So if we plot it, we can see that it's a very noisy signal. It has rapid changes that cannot be represented by the basis vectors. This that I'm showing here is exactly this R. So we have V, that is a noisy signal. We have R, that is only the noise. And Y, that is the noise-free signal. Just the error, or the residual is also called. That's not an assumption, that's something that it will be always be satisfied. Yes, because the vector is going perpendicular to the plane or the generated space. So this R is always perpendicular. Yes, it has a length and it's going up. And depending on how we create our space V, more noise can be represented by this space or vector space. So let's put it again. This is the same as saying that we have our vector B, that is the noisy signal. Then we have our Y, that can be represented as a linear combination of the basis vectors. And this Y is only the smooth part. And perpendicular to this, we'll always have the residual, that in this case is only the noise. So this is a relation between all of these vectors and matrices and all of that stuff we have seen in class. And signal processing, we basically represent a function as a vector, and then we apply all of the properties and optimization functions, problems that we had, and we can, for example, remove completely the noise. Okay, so I'm not sure how many of you know why I choose this basis exactly, and does the least squares maximize the signal to noise ratio? It depends. No, not necessarily. It depends how you create your basis vectors. As I said, the basis vector can include the higher frequency components, and therefore can represent the noise. And it will basically the orthogonal projection will be very similar to this. So it's not a way to maximize the signal to noise ratio, but we can find a number of vectors. For example, here I choose 3 waveforms, and obviously if I put more and more waveforms, there's a limit in which I am maximizing the signal to noise ratio. Depending on how many I put, or how many basis vectors I put, where do I do the cut, I can change the signal to noise ratio of my denoise signal. If I put too much waveforms in the basis, my space can represent basically everything, so my denoise signal will be basically the same signal. If I put too little, the signal I obtain will not be the same as the original one. For example, if instead of cosine, I choose where is it? Here. So instead of cosine, I choose 1 plus cosine, and I create my here. I'm on purpose deleting the frequency 0, and I do the same problem, the least squares problem. Why this, and then plot this. You can see that my denoise signal is basically the same as this one, but it has an offset. This is a way to show that depending on how many vectors or what vectors I choose, I can have a totally different signal. So here what I did is that I added basically a constant to the signal, but in my space I didn't add a constant vector. That way, in my space, constants cannot be represented, and therefore when I solve the least squares problem, I obtain a signal that is basically centered in 0. So depending on how many components I use, I can be representing the signal correctly or not. That's for you to decide which model or in which space you want to obtain the signal. So let's put it back. This. And this. Another interesting thing about the space I choose for this is that if we see the coefficients, you can see, maybe this is not the best way to plot it. Where I'm importing plot. It doesn't matter. I can do it again. Matplotlib.py plot import stem. Stem. So now if I do a stem of x, I can see that I have components in f, that it was the frequency equals to 0, corresponding to the constant part of my function. In 1, I have 0 components. In 2, I have more. And then basically all of the other components are 0. Do you know what is this called? Or the name of this plot? No? Well, I choose the sine or cosine basis functions because they have a special property. And the special property is that if I add enough of them, I can represent all the signals, basically. In this case, I'm using cosine functions to represent even signals, but you could, for example, use sine functions to represent odd signals. But if I add enough of these cosine and sine basis functions, I can represent any signal. And actually, if instead of using cosine functions, I try to use sine functions in this case, and do exactly the same as before, plot here. So you can see that my denoise signal is basically only the noise. It can't represent the signal. So be careful of the space that you are choosing, because, for example, my signal here was mainly even, and I tried to do a fitting with only odd functions. That means that my problem will always fail to represent the signal. And when we add this together, cosine and sine, they both can represent all the signals. And the plot that I showed, being this one, let me do the same with cosine again. Cosine, list of squares, y, plot this one here. Okay, so this, can save the figure pictures. Can put it here. Whoops. And now if I plot x, is here. I do the same. This is figure 2. Can I rotate? Well, it doesn't matter. And if I do t comma a, I have all my functions, but let me remove some of them. Maybe I removed too many of them. Let's see. Yes. This. Okay, that. Let's remove a little bit more. Okay. Maybe more. Yeah, there is better. Okay, so show. Let me save this to figure 3. But this is a figure 3, sorry. Okay, so we had basis that is composed by cosine and sines. Here I'm showing only with cosines. I had my coefficients here in that I have frequencies. For example, this is frequency 0, this is frequency 1, so on. This is the magnitude of a coefficient x. This is x. And each of these functions here are, let's say, v1, v2, v3. So v1 goes with x1, that is this. So the constant function is represented by this coefficient. Then this one here is a cosine with a higher frequency. This one here is a cosine with a higher frequency. That is exactly the one that matches this. And then the other ones are higher and higher. And this one is like too many ups and downs to be represented by this. Okay, so I was asking if some of you knew how this plot here was called, because when you try to do signal fitting by using cosines and sines, basically the vector of coefficients, or this plot here, it's what it's called the Fourier transform, which says how many of each frequency I need to represent my signal. Have you heard of the Fourier transform? So this is very used in signal processing, the Fourier transform, because as I said earlier, you can represent with cosines and sines all the functions. With the cosine functions, I can represent the even parts, and with the sine function, I can represent the odd parts. And when combined, I can represent all the signals. Another way of writing this is that instead of using cosine and sine separated, I define a basis is of k of t, that is cosine plus sine. But this sine is multiplied by an imaginary part. Do you know what an imaginary number is? But it's basically an extension of the real numbers, in which, for example, you have 1 plus 2 times I, and the imaginary part is always separated from the real part, and this imaginary part is defined as the square root of -1. And the complex numbers are useful because you can represent basically the solution of more equations with them. With real numbers, for example, you cannot represent the solution of this equation, but you can do it with complex numbers. And that also applies to functions, and you can define functions with real and imaginary parts. In particular, in the Fourier basis, we use that. But the only relevant part is that this can also be written as the complex exponential that maybe you have seen before. But don't be confused by this. This is only a little detail. What I want you to understand is that with cosine and sine functions, you can represent every function. And the coefficients after you do a decomposition in the cosine and sine basis of a function is called the Fourier transform. That means that the signal can be written as these coefficients x times the functions b's. that is the same as x1, x2, xn, b1, b2, bn. Dot 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 here. You can see that another benefit of this representation in sinusoidal bases is that our problem or our function can be represented with just a few coefficients. You can see that in this space, or the time space, you need basically 100 coefficients or samples, but in this space, the Fourier space, or the frequency space, you need only 2 samples to represent the signal. So you can see maybe how this can have an influence in compression. You can, for example, have a signal do something that is called the Fourier Transform, then only save these 2 coefficients instead of 100. Yes. The height of each of these coefficients represents how much of this signal or this frequency is in the starting signal. So for example, here I have a contribution of 1 to the constant signal. That is because it is the phase to have an offset of 1. And then you had the other signal. That is basically the one in yellow or orange. So we don't have more time, I think. I just wanted to show you a little bit how the least squares problem can be related to signal denoising, and in particular when you use the basis of sinusoidal functions, or that can represent a space that is useful and is useful for many reasons. One, that we can represent the signal with a few components, and another one is that this frequency space could be the thing we are interested in from the first time. For example, in electrocardiograms or electroencephalograms, the brain has different frequencies in which the neurons react. Each of these bands of frequencies represents something different to be analyzed. And with this procedure here, you can separate in the different frequencies and analyze basically which one is higher. For example, if this frequency here represents concentration, I can see how this coefficient changes over time and see how the concentration of the patient or volunteer is, etc. This is just a little introduction to signal processing. And the cool thing about this is that you can represent the Fourier basis, or the basis with sines and cosines, by a matrix, but you can also represent it just by a function or an algorithm. And that's where the adjoint is more useful, because this matrix could be very big. Let's say, for example, in this case it's not very big, but here is 100 times 10. But depending on the case, for example, in 2D, to analyze 2D signals, the matrix A increases in size exponentially. And that's why we can represent linear operators not by only matrices, but with functions. And there are some functions that have a transpose. And in the case of the Fourier matrix, the adjoint or the transpose is the same as the inverse of the operation. And we have functions that already implement the inverse and the direct transformation very efficiently. In practice, what that means is that we can replace a very big matrix with a tiny function. And that's why the adjoint is important, because we need to verify that the adjoint properties are satisfied with these two functions, and everything should work fine. Maybe the last part was a little bit confusing, but basically have that A, the matrix A, can be very big. So instead of using all the components of A, we can replace A by a function. And by a function, I mean like a function in Python. For example, for the Fourier transform, you have something that is called FFT. And instead of having the big matrix and doing the transpose or the inverse, that is a very inefficient process, we can have a function that does that for us. For example, in the Fourier transform, we have an inverse that is the inverse Fourier transform, or the inverse FFT. FFT is the algorithm. The function or the that is trying to do is the discrete Fourier transform. Because we have multiple types of Fourier transform, and here the inverse is the inverse of the discrete Fourier transform. The FFT is the algorithm, and the DFT is basically the representation or the transform. So we can replace our matrices with algorithms or functions, and we do not need to save or calculate the transpose or the inverse of a very big matrix. Yeah, so the adjoint concept extends to basically things that can be represented with any function in Python that is linear. So for every function that is linear, we can have a direct and a transpose. Not necessarily an inverse, but at least we have a transpose. Okay, so any doubts, or did you get what I was trying to talk? I have a few minutes for questions. Okay, so if you want to know more about Fourier transforms, I encourage you to watch 3 blue, 1 brown. This video, what is the Fourier transform by 3 blue, 1 brown. It's a very good video. I will put the link in the chat. And this Fourier transform is a core concept of signal processing, and I'm not sure if we'll have enough time to see it, but at least I want you to know it or have seen it before. Sorry, I sent the link to it only to Jorge. Yeah. When you choose a frequency of 100, maybe you can represent the noise, and I believe that is not convenient, or just with to function is enough. I'm not quite sure if I understood your question correctly, but all the signals can be represented by cosines and sines. Here I cut the frequency until 10, but if I did more frequencies, for example until 50, instead of having a denoise signal, I will have exactly the same signal, but represented with cosines and sines. We can do that, but I'm not sure if we have enough time. Maybe try to do it in as a mini homework. You can change the code and see what happens if we put more frequencies, but basically the same. We'll be fitting to the noise. So that's why it's more ideal to use less frequencies than more to do a denoising. The procedure that we did here, basically, as we remove the higher frequencies, was a low-pass filter. As we cut the frequencies until one point, for example f0, and we remove all the high frequencies, our orthogonal projection of the noisy signal is basically the low-pass filter, or the low-pass filter version of the noisy signal. And just to, I don't know, incentivize your curiosity, you can have actually a connection between the convolution, that was an operation that we did to do the low-pass filtering, to an operation in this frequency space. This is the time space, and this is the frequency space. In the frequency space, deleting the frequencies higher than something is equivalent to doing filtering with a low-pass filter. And there's a relationship between both, but if you're curious, you can Google it, or maybe in the 3 blue 1 brown video is explained. But basically you are transforming a multiplication in the Fourier space, and in the time space that is equivalent to a convolution. Okay, that's all we have time for today, so I'll stop the recording. If you have more doubts in Spanish, you can solve them after stop the stream.